Hey guys, welcome to the next physics lesson, and today we're going to talk about this is part 2 of our previous lesson, and again we're talking about kinematic graphs. Okay. So this time, let me just scroll up a bit. Okay, this time we're going to be talking about graphs that have some sort of acceleration to them. So let me just write the title out first. Okay. So last week we talked about graphs that were all had constant slopes, where there were no curves whatsoever, and all the velocities were constant everywhere, like they're all straight lines with no acceleration. And remember, this was a position time graph. And then we converted this to a velocity time graph by finding the slopes at each segment, right? 1, 2, and 3. We found a slope at each of these segments. And why did I draw displacement here? Let me just erase that. I didn't mean displacement, I meant velocity. So this is a velocity time graph, and we converted this to that. So again, we divided into the same 3 segments, and we found that let me just extend this. So we found that the slope was whatever, and it was like somewhere here, and the slope here was 0 because it's a horizontal line. Actually, I'm going to do it in a different color. So it's a straight line here, and it dropped vertically down to 0, and then it dropped some more vertically down to some negative slope, right? Okay, and then what if we go one step further this time? What if we bring this graph, after bringing from this graph to this graph, let's bring from this graph to an acceleration graph. How would we do that? Same thing. Acceleration is the slope of a velocity time graph. So let's find the slope at each of these 3 segments. And what do we notice? Well, let's divide it into 3 segments. Okay. What do we notice? The slope here is 0, the slope here is 0, and the slope here is 0. So the acceleration for the whole graph is 0 at all times. And this is consistent with what I told you guys, because when we have a graph that has no curve whatsoever, there is no acceleration, and when there's no acceleration is 0. So this ties in well. Now, what happens if we have a graph that has a curve? So for example, let me draw a huge one right here. Okay, what if we have a huge one like this? And what do we have? Okay, so let's say I'm going to draw a position time graph once again. Okay, so what if we have a graph like like this? What would this look like? And it's not actually going down, it's just going up like that. Okay, like that. So what would this graph look like when we convert it? Now, without calculus, we can't actually find what the slope is for the whole graph, like what the actual slope is, or what the so like we can't actually find the actual graph of the velocity time graph, but we can approximate it, right? We can actually approximate it. Like we don't need calculus to be that exact. So let's approximate it. So once again, let's recap. How do we convert from a position time graph to a velocity time graph when there were only straight lines? Well, we broke it up into segments, and we found the slopes at each of these segments. But look at this graph. How can we break it up into segments? Well, we can just use the start and the end points as these segments. So we can say that this whole thing is a segment. So, and I'll show you how this ties in later. Just bear with me for a second. So let's transpose this into some sort of a velocity time graph, right? Okay. And let's say this is like at time 5, right? And this is again at time 5. Okay. So how would we convert this? Well, we can say that without giving any values to it, I'm just going to give you a rough idea of how it's going to work out. So the slope at the start, what is it? I'm going to represent the slope as a blue line. What is it like? Well, the slope, remember, the slope at this point is called the instantaneous velocity. And what this means is that, what does instantaneous means? It means at this instant. What is the velocity. So instantaneous velocity means the velocity at that instant in time. So at the very start, at time at t equals 0, what is its velocity at the very time? And we can see that the velocity at that time is quite steep. It's a high. So we say at t equals 0, velocity is high and positive. It's high. I'm gonna say, okay, I'm just write high. So it's high and positive, right? Okay, and that's v1, and we'll call this v1. This point 1. How about point 2? What is its velocity over there? What is its instantaneous velocity at the end point? Well, if we draw an instantaneous velocity, and remember, to draw an instantaneous velocity, we draw what we call a tangent. Let me write that down. We draw a tangent. T-A-N-G-E-N-T. And what a tangent is a line that only touches the graph at one point. So I'm going to just give a brief lesson, a quick short lesson here on what a tangent is, for those of you guys who do not know what a tangent is. Let's say a tangent at this point. What would the tangent be at this point? Well, it's just this line, because the tangent is a line that touches any given line, any given figure at just one point. Look, if we actually zoom in on this point, we would see that it only touches it at one point, at one specific point. So if we have a line like that, and we want to find a tangent here, we would say that the tangent would be something like that, right? It's one line. Oh crap, that's a bad line. One line that touches it at just that one point. So let's go to this graph. What is the one line that touches this graph at just this one point? Well, it's something like that, right? Something like that. Now this is just an approximation, and you don't have to be too exact. All you have to know is whether it's positive or negative, and if it has a high or steep slope. I mean, high, steep, or shallow slope. So v2 at t equals 5, v2 is low, so it's like its slope is pretty low. It's almost 0, and it's positive because the slope here is still pointing upwards. Remember, when the slope is like pointing from lower left to upper right, it's positive, and when it's upper left to lower right, it's negative. And in this case, it's pointing from lower left to upper right, so it's positive. So here we have it. We have what the starting and end points are, and let's graph it on the velocity time graph. So at t equals 0, what is its velocity? It's somewhere at t equals 0. Its velocity is somewhere high and positive, so it's somewhere here at the high end of the velocity line. It's somewhere high, and it's positive because this is the positive side here, and the below, and somewhere below here. So if we extend the graph further on, it will be negative, right? So we know that v1 is high and positive. How about v2? It is still positive, but low, so it will be somewhere around here. Okay, now how do we actually draw this line? Well, it basically, what is the slope at each point? So we can see, you draw a slope at this point, at this point, at this point, at this point, at this point. We actually drew it all out. We can see that the slope gradually gets to the end slope. So it starts off at this slope, and it gradually gets to this point. So the slope gradually grows smaller. It gets less steep each time you go up. So it starts off high and steep. It starts off steep and positive, and as you travel along the graph, it gets less steep but still positive. So what can we say about this graph? Well, it's going gradually until you get to this slope. And there we have it. This is how you convert approximately, because we don't know calculus yet. This is how we convert a position time graph which has some sort of acceleration into a velocity time graph, and we just draw a straight line down, because you can see here that the slope just gets, from this, it just gradually gets smaller until it reaches that kind of slope. So instead of breaking up into parts like that, to convert a line that has a curve, you would find a slope at as many points as you want. The more points you find a slope off, the more accurate it will be. But general rule of thumb, you just find the slope at the start and end points, and just draw a line connecting those two. So we find the slope of the starting point and the slope of the ending point, and we just draw a line connecting those two. Okay, but now, what if we convert? Well, let me just erase this part that I just drew on. Okay, what if we convert this now into an acceleration time graph? What would it look like? Well, what is acceleration again? How do we convert from a velocity to an acceleration graph? Acceleration is the slope. Acceleration is the slope, and remember, slope means m is slope. M stands for slope. So the acceleration would just be the slope of a velocity time graph, right? So what is a slope? Well, again, we can't, since we had no values for this graph, we had no values for this graph, so this whole lesson is just abstract. I'm not assigning any values to this graph just yet. I'm just showing you how to, given a graph with no values like this, how you convert a graph. So with no given values, how would we convert this to an acceleration graph? Well, the same method we would do for a position time graph, which has just one line. Find a slope and graph it as a horizontal line. So slope, you can say that the acceleration for the whole time period is negative because it's going from upper left to lower right. So it's negative, and what? It's somewhat steep. So we call it it's somewhat steep, right? And it's all approximated, so it's negative, it's somewhere here, and it's somewhere steep. So draw a line down again to denote where 5 seconds is, and we draw a line like that because its acceleration is constant, because the speed is decreasing at a constant rate at each point in time. Because since it's a linear graph, the slope is constant at all points, and since it's constant at all points, its acceleration must be constant at all points in that time period. So since it's constant, we just draw a horizontal line because at each point in time, the acceleration is constant. And that's how you convert a graph like that, a curved graph, into ultimately an acceleration graph. Okay, now let's do some exercise. Given now that you've learned how to convert, what if I give you so now this is just review, right, of what we've covered the whole past 2 lessons. How would we convert given a displaced position time graph? So I'm just going to draw a few graphs, and I'm going to give you some time to work it all out. Okay, and we are back. So these are the graphs I drew for you guys, and I would like you guys to just take a moment right now and just pause the video for about a few seconds. Just pause the video for now and try to solve these graphs. Like, try to convert it to a velocity time graph, and if you want to try to go the extra mile, try to convert from that to an acceleration time graph. Just so pause the video right now, and I'll explain it in a bit. Okay, hopefully you guys paused it. So let's do number one. Okay, now we're doing it in the velocity time graph. So how would this look like in a velocity time graph? Slope, remember velocity is slope, so what's slope? It's 0. So the velocity here at 1 would just be a horizontal line on the x-axis. Easy. Number 2. What is it? What's a slope? 0. Because it's still a straight line, right? It's still a straight line. The slope of a straight line is 0. So again, 0. How about 3? How about number 3? What's the slope of 3? What's slope? Well, it's something a bit steep, and it's negative. So it's negative. So let's draw it here. It's somewhere in this region, and it's pretty steep. So it's about here. And let's use blue again. And so the line will be here. And since it's a linear slope, it's a line again. It's constant throughout. Okay, how about number 4? How about number 4? Number 4, it's a curve like that. And what I say about curves like that? Well, we would just find a slope at the start and find a slope at the end and connect those two dots. So what's slope at the start? It's something negative, remember? How we find a slope at for a curved graph, we find the tangent, and the tangent here is something high and steep, really steep and negative. And then at the end, it's something still negative, but almost 0. Well, we can say 0. Let's say that this is at 0. At the very end, it slows down to a 0 speed. So let's say this is 0 at the end. It's horizontal at the end. So it goes from something high and positive to 0. So it went from, let me just extend the graph. It went from something like something high and positive around here to a 0. So let's draw the graph. Something high and positive to 0. And this is how the graph would look like. How about number 5? Let's see. Once again, we draw the tangents for the start and the finish. Start is at 0. At the end, it's at something high and positive. So again, draw the graph. And at the start, it was 0. So it started at 0. And at the end, it was something high and positive. So it's in a positive region, but high. So on here. So we can say that the graph is something like that. Okay. Now, how about number 6? How about number 6? Oh, what did I just do there? It's a V. It's a V. How about number 6? Again, we draw tangents. It's 0 here, high and negative. So 0, and then high and negative. Let me extend the graph. 0, it starts at 0 and ends up somewhere around here, high and negative. So the graph would look like this. Awesome. So if you've got these graphs, you're doing fine. And let's say you want to convert these graphs to an acceleration graph. Well, it's pretty standard. So this one, any of these 3 graphs, any graph that has a slope of 0, the acceleration would just be 0. Would just be here. So these 3 graphs, the first 3 are easy. How about the last 3? Well, for this one, the slope is positive and mildly steep, so it will be somewhere like that. And it's linear again because it's a straight line and it's constant. How about this one? It's the same as this one. Slope is positive still, and it's mildly steep. How about this one? This one, it is negative now and somewhat steep. So let's draw the graph like that, and it's somewhere like that, right? I'm gonna use blue actually. So it's like that, and like that. Okay, and that's it. So last challenge of the day: convert this graph into a velocity time graph. Now take a few seconds and solve this on your own, and pause the video. Okay, hopefully you guys paused the video. I just love doing that. It's like, hopefully you guys paused the video, and it'd be awkward if you guys didn't pause the video. But whatever, let's move on. So once again, without the lines, I just drew the lines to help you guys visualize how you break them up. So if you have a graph like that, how would you convert this somewhat looking complicated graph into a velocity time graph? Well, once again, split into easier to manage segments and go on from there. So let's name this A, B, C, D, E, and F. How would you graph this? Once again, find a slope at each segment. So the slope of A, it is high, and positive. So it's something like that, high and positive. So B, let's say this is a horizontal line. So it'll be at 0. Actually, I should use blue. High and positive. At B, it's 0. Right? At B, it's at 0. At C, now remember this kind of graph, it's a curve. And so it starts at 0, going all the way to somewhat high and positive. So somewhat from here, so from 0 to go somewhat high and positive. So it'll be someone like that. Approximately, like all these are approximate, like, because since we have no values given, we're just doing approximately, right? And then from there, it starts off from this point and goes down to about a 0 velocity, because the instantaneous velocity at this point is about 0, because it's horizontal. So it goes all the way back down to 0, and then now we're at this part E. From 0, it goes all the way down to somewhat high and negative. So it's somewhere here. So it goes all the way down, somewhat high and negative, and then from here to there, it slows back all the way down to about a 0. Let's just say it's at 0. I just didn't draw it properly. Let's say it goes like to it's like a horizontal line. So it's at 0. So it goes from somewhat high and so it goes from a point where a slope is somewhat high and negative to 0. Oops, that was bad. Like that. And I forgot to draw this. Okay, so this is how a graph will look like. A, B, C, D, E, and F. And let's compare. A, B, C, E, F. And this is how the graph would look like. So hopefully you guys have an idea of how converting a position time graph to a velocity time graph works out. And now, yep, that's about it for this lesson then. And I'll see you guys in the next episode. See you then. Peace out.